I'm an ecological engineer, I guess you'd say. I spend my days designing and building and operating constructed wetlands, particularly for treating wastewater and dealing with polluted waters. That's my focus. But with this presentation, rather than focusing on technical details so much, I've sort of posed a broader question of, can wetlands help save the reef? So I'll focus particularly on the Great Barrier Reef catchment aspect, looking at a somewhat high-level kind of approach to what sort of scale are we talking about to actually address nutrient issues, how much wetlands might we need in terms of constructed wetlands or restored wetlands, what might that cost, is that even, are we just dreaming here, and what sort of scale, I mean on a high order of magnitude sort of level are we looking at. I'd like to just also acknowledge Sarah Costello, who helped me in the preparation of this presentation and pulling together some information. The purpose is really to give a bit of an overview of water treatment wetlands, what they are. We'll hear more and more about that during the day, but being the first sort of cab off the rank about constructed wetlands, I'll give a little bit of an introduction there, and then to look at a bit of a high-level feasibility evaluation of how feasible is it to consider constructed wetlands in catchments, agricultural catchments, to solve some of the issues. And I'll look at nutrient and pesticide reduction at a very high level, and some of the climatic issues, rainfall and runoff, suitability. I'm going to focus on nitrogen removal mainly, and I'll look at example catchment, the wet tropics catchment, at a high level, look at how much wetland might we be talking about to achieve the nitrogen reduction targets that have been set in plans. Also to look at, and we're talking about a big problem on a major scale, on a landscape catchment scale, so to look at what can we learn from, are we the first ones to sort of try and tackle this problem in the world? No, of course not. There's quite a number of other sort of ambitious or equally ambitious case studies from around the world that we can maybe learn a few lessons from. So we've had a look at some of those. So what is a treatment wetland? And I use treatment wetland, constructed wetland, I suppose, interchangeably. We're talking about engineered constructed wetland systems for the primary goal of treating or improving water quality. Basically a type of system where we're aiming to harness and take advantage of natural processes for the purpose primarily of improving water quality in whatever application that might be. And we could generally categorise them as being technically and operationally simple, and this is a big selling point whenever we're trying to sell wetlands. But they actually, in detail, and as we've heard already a bit this morning, they involve a very complex interaction and range of processes between water, soil, vegetation, like microorganisms, and gaseous interactions with the atmosphere, and biology, chemistry, and physical processes. If you're looking at trying to understand what's happening in a system, very complex, keeps scientists busy trying to understand and define processes and so on. But from a black box kind of level, in terms of operational compared to mechanical treatment systems and other technologies, then they are relatively simple to operate and simple to build in many cases. Like I said, spend my time designing systems to treat and solve different water quality issues. So I like to talk about my treatment wetland toolbox in a way, because we're not just talking about one type of technology or system. As you can see here, there's several different wetlands, constructed wetlands come in different forms and shapes and sizes. We have what we call surface flow systems, where the water's moving through the stems of plants. Subsurface flow systems, where you might have a bed of gravel, where water is passing through the gravel and the root zone of the plants, receiving treatment. Systems that go horizontally or vertically. And these all have different pros and cons, strengths and weaknesses, different processes. Some are more aerobic than others, some are anoxic. So depending on what we're trying to achieve in terms of treatment and what other limitations there might be, then we go to our toolbox and piece together a treatment train or a system to do the job. And we also have then get into the range of more aquatic systems like ponds without actually emergent vegetation, free-floating macrophytes in some cases, or floating treatment wetlands where the emergent plants, like we have in these systems, actually floating on a created mat or buoyant raft, getting some of the advantages of ponds and wetlands into the one system. As you can see, there's a whole range of different technology options available that do different things and are suited to different purposes. And often we'll be integrating those in different ways to solve a particular problem. If we look at agricultural catchments in particular, we might see ponds and sedimentation basins or lakes systems being used because of the large volumes of flow and runoff we're dealing with. Because we have typically if we look at the rainfall here from Cairns throughout the year from several different years, you have very high variability of rainfall, which results of course in high variability of runoff in different catchments through different seasons and through different years. So it's a very complex hydrological situation to deal with, which then focuses us in on what type of wetland system might be most suitable. Subsurface flow systems have a limitation of a gravel media that you're trying to force the water through, and generally limited in terms of trying to deal with big extreme ranges of flow variability. And it depends how we might approach things as well, depending on the flow variability, whether we're trying to capture first flushes in particular. Design a system to treat all of the flow is generally not realistic, so we might have then high flow bypass systems in runoff-based treatment systems. And in a general sense, in terms of wetlands, then we'd say surface flow wetlands or free-water surface systems are typically the most suitable for this type of variable flow runoff-based systems. This is actually an example of a big constructed surface flow wetland system that I spent the last 4 years working on in the Middle East. It gives you an idea of, they can be very big, they can be very small. This is a typical system layout or section through a runoff type of stormwater or agricultural runoff constructed wetland system, where we might have a sedimentation pond or a basin up front to capture a certain portion of the sediment flow before it gets actually into the wetland, because then it's easier to remove from that system. Deeper zones and shallower zones where we have dense vegetation growth, wetland plants, and water flows through, and then an outlet structure to control water levels and maybe get some peak flows, extended detention in the system. This is an example of an actual system in New Zealand that's treating dairy drainage water as it runs off. This is a dairy farm, nice and green pasture, pond sort of system followed by a surface flow wetland, and you can see the creek running in the background. This is an example. I'll just touch briefly on pesticide removal in constructed wetlands. I won't go into too much detail because it's a complex field in itself, and there's also, I would say, limited data and knowledge and experience about pesticide transformations in wetlands, or it's a growing area of understanding. Removal rates vary quite substantially. We've got a range of removal processes. Hydraulic retention time can be an important factor. And if we extrapolate some of the findings out of monitoring that's been done or performance evaluation, you can sometimes see that the dense vegetation can increase the effectiveness of the process, but these are fairly broad generalisations. There was a review paper published by Jan Wimmerzaal and Brezanova last year, and they basically reviewed what literature and reports they could find looking at pesticide removal in constructed wetlands. It's actually a very broad topic to try and summarise even into one graph, but they did that. You can see, the take-home message is for a range of different pesticide chemicals here, which are all very diverse in themselves. Here's percent removal, and you can get very high removal, and you can get lower removal for other pesticides and chemicals. But what's hidden behind this is that this doesn't tell us anything about how each system was maybe loaded, what the loading rates were, what the retention times. Percent removal is a very kind of coarse brush with which to try and look at such data, but it's an attempt, and at least it's showing that wetlands can remove pesticides. That's a positive thing. If we look at nitrogen processes in wetlands, we've already heard quite a good explanation of what it looks like in an agricultural catchment. The process is the cycle is the same in a wetland. It's again fairly complex relation between vegetation, soil and water and microorganisms and biochemical processes. If we summarise that down and look at surface flow wetlands, then we'd say the key nitrogen removing processes or transformations You have plant uptake, which tends to be a relatively minor proportion of actual removal because it will tend to die back and cycle within the system, and harvesting is normally not particularly commercially viable. You have nitrification, which is basically conversion of ammonia to nitrate when we have oxic conditions, and denitrification of nitrate into nitrogen gas and loss from the system. Generally find, especially with agricultural systems, that the plants play an important role in providing carbon to actually drive the denitrification process, because often agricultural drainage or runoff water can be carbon limited or poor in terms of denitrification. Here's some typical removal rates that we see from surface flow wetlands treating agricultural runoff, particularly that's dominated by nitrate and limited in carbon. Quite a big range in terms of kilograms of nitrogen removed per hectare per year, but that's the sort of experience base. The range is actually bigger than that if you go into every different study, and that depends also on loading rates and the characteristics of the runoff and the catchment and the concentrations that we're dealing with and so on, and how peak and flashy the flow is and how much you're actually capturing in the system. It's complex, let's say, but there's a range of performance to start with. How much nitrogen do we need to remove to save the reef? This is the big question, and there's plenty of other people better equipped to answer the question than me. So I've looked at what other people have said and looked at focusing on one example catchment, and this is just a high level sort of approach at looking at things. The wet tropics catchment, the dissolved inorganic nitrogen load in the catchment is estimated and measured to be around 4,400 tonnes per year of nitrogen coming off the catchment. Nitrogen removal targets that have been set, if we look at 80% reduction in that amount by 2025, because 2018 is almost, we've missed the boat there a little bit. So that's a reduction of about 3,500 tonnes per year of nitrogen that needs to be removed from that catchment in order to achieve these targets to improve the water quality to protect the reef. Big numbers. Major sources of nitrogen in that catchment are particularly cane farming. It's about 41% of the catchment is cane farming and so on. That contributes, so a significant contribution of nitrogen in that case. So let's have a look at the question of how much wetland would we need to actually achieve that target. The load here, again, from the catchment, and if we're wanting to achieve that 80% target by 2025, we need to remove about 3,500 tonnes per year. If we assume, for argument's sake, that we want to hit about 40% of that target using wetlands, because wetlands, I'm a wetland fan and obsessed wetland person, but I'm not going to stand here and tell you that wetlands are going to solve all the problems. So let's pick a number of 40% of that target. We need to basically remove this number, this many tonnes per year through wetlands in this modelling example. So the treatment range I've chosen from 200 kilograms per hectare per year nitrogen removal up to, let's say, 800. So it's a bracket within that broader range that I talked about before. This gives us some hectare areas of wetlands that we would need to achieve 40% reduction of that target value. We're looking at somewhere between 1,700 to 7,000 hectares of wetlands needed to be either constructed or restored or put in place into that catchment to make a significant impact on achieving those targets. I've picked a number here in this last table where we're looking at 400 kilogram per hectare nitrogen removal per year as a middle point between these ranges, because otherwise we'd just end up with too many ranges, too many numbers. That equates to 3,500 hectares of wetlands. The sugarcane total area is just under 200,000 hectares in that catchment in the wet tropics. So an interesting number is, okay, that's about 2% of the cane farming area in that catchment. Even though it's a big number, it's a lot of wetland, it's still actually a relatively small part of that farming catchment. I'd be a bit alarmed if it was 20% or something, then I might as well go home. But 2% is somewhere within the range, and as we'll see, of typical experience in other agricultural and even stormwater catchments. I guess, is this too ambitious? I would say that stranger things have happened. For example, building 700 hectares of constructed wetland and ponds in the middle of the desert in Oman to treat 115 megalitres per day of oil field wastewater. If we can do that, then I think we can do almost anything. So this is, just to give you an idea of scale, we've got about 3 kilometres in this direction, 3 kilometres in this direction, constructed wetland system. I would say anything is somehow possible, and we shouldn't shy away from ambition, especially with such a big challenge ahead of us. I'll now look at just a few case studies from around the world and in Queensland, particularly in Sweden, where they've had similar issues trying to solve eutrophication problems from agriculture. New Zealand, dairy drainage is a big issue there. And Mullaney, where we did a project a few years ago. And in the handout or the information that will be available online later, there's a series of other case studies that I looked at, including the Everglades, where they basically, Congresses probably 20 years ago or so now, put $10 billion towards restoring the Everglades, big area of wetlands, 15,000 hectares of agricultural treatment wetlands just as a part of that, and a lot of that sort of shows if you put the money behind it and government and the policy makers get behind things, then anything is possible again. The Mississippi, Ohio, Missouri River Basin, which drains the majority of the US and particularly the agricultural sort of breadbasket through the middle, drains into the Gulf of Mexico, drains nitrate basically in there and has caused massive hypoxia of the Gulf of Mexico. People have looked at that and what would be needed in terms of wetlands there, and it's around 200 to 400,000 hectares to reduce the nitrate by 30%. Interesting point there is the target is actually 40% in that case that they think is needed. To get that extra 10% is basically an order of magnitude increase in the amount of wetlands and riparian restoration and things that would be needed. Let's have a quick look at Sweden. The approach that they took was to look at multifunctional wetlands. So not just the prime goal was to remove nutrients, but they also acknowledged and appreciated the other values that wetlands provide within the catchment. The Baltic Sea was the issue. It's a fairly closed water body and leaving a lot of runoff from agricultural areas in the Scandinavian countries. They defined the target was 12,000 hectares they needed to reinstate or restore wetlands in a 10-year period. So we've got an example where we can see, okay, that was an ambitious goal. Did they actually achieve that or not? It was partly funded by the EU and directed in a way by the EU Water Directive Framework, which in a policy governance level, there's actually a high, even level above federal government in that case, which is driving things and providing a bit of a stick and has the authority to penalise countries for not meeting their water quality targets and providing funding at the same time, so not just penalising but funding things. But it was also funded at different levels right down to local government and community groups and NGOs and action on all those different levels. The target that they were trying to reduce per hectare per year is here. They actually achieved 7,000 hectares of restored and created wetlands in that 10-year period, which didn't quite hit their target of 12,000, but it's an impressive feat nonetheless. There's a lot of data and monitoring from systems in that case, which give us some useful kind of nitrogen removal performance data. And what they found was also many other benefits that came from doing this from the wetlands other than just nutrient reduction. A key point with all of these case studies really is that you need strategic catchment level or bigger planning to identify a clear strategy of where to target what areas where to invest your money and effort and where the hotspots are and all this. And if we're looking at the reef, it's all about really having that strategic planning and approach, in my opinion, to say, okay, we know wetlands can do a job, but where are we going to get the biggest bang for our buck? And then we can set about implementing them, part of a strategy or a solution. Technically, building wetlands is easy from my perspective, and we know that they work and do a job. If we look just quickly in New Zealand, they have issues, a lot of nitrate coming off drained pastures in dairy farming. So they've for years have been looking at different options, and wetlands have played a big role in that. So we get data out of there as well. Interestingly, it's a big range, but from somewhere between 0.1 to 5% of the catchment area, contributing catchment, would need to be converted to wetlands to achieve their targets. And that depends on the catchment and different factors, why there's a range there and how efficiently performing those wetland systems are. They've looked at strategic planning of where to put wetlands. An interesting point that comes out of that sort of work is whether you focus on small on-farm wetland systems that are sitting somehow on farms, dairy farms in this case, and collecting runoff directly near the source or intercepting drains before it gets into a creek or a gully, or is it going to be more effective and efficient to build bigger wetlands lower down in the catchment? And where do you get the biggest bang for your buck? And it's also completely different political governance and land ownership and funding situations depending on where you're working. If you're expecting farmers to do the job on their property and give up some of their land, or further downstream, then you've got opportunities for state government, for example, or local government to actually buy back marginal land or convert those areas to bigger wetlands that might have a more effective benefit. If that's all we've got time for, I'll just flick through maybe the lessons from these case studies which we've touched on, and you can read the presentation. So we've got wetlands can remove nutrients, of course, and retain sediments, pathogens, pesticides within agricultural catchments. We get a range of performance. It's going to equate to fairly large areas of wetlands that need to be built to play a role in achieving some of our reef targets. But that may equate to a small percentage of the actual contributing catchment area. Often we find that bigger wetlands lower down in the catchment are more effective because they can be more optimally optimised in terms of design and engineering. It's cheaper per hectare to build one big wetland than to build 100 small wetlands. In some cases, better sort of flow attenuation by the time you're getting further down the catchment compared to higher up in the catchment. But this is still an open question, really. An interesting point to finish on probably is this last table. If we go back to that high level sort of look at how much wetland we might need to achieve 40% reduction of the 80% target. So this area of wetlands, and depending on what sort of to build a wetland in this situation, it's difficult to put a number on it because it's not a product off the shelf, but anywhere between $30,000 to maybe $300,000 per hectare, depending on the scale and size and so on. So that's somewhere between $100 million and $1 billion to achieve that 40% reduction in the wet tropics catchment, just one catchment. That's the figures. They can be tweaked and argued around and so on, but we're not going to get there by just fiddling around, and it's going to take investment and money, I would say, to achieve the goals. Thank you.